Okay, so picking up where we left off here, we had found that -1 and 1 were the crucial points of the second derivative here, and so we put them on the graph. There aren't any discontinuities, so we don't need that. All right, so let's plug in values, and again we said that it all depends on 1 minus x, 1 plus x, so if I plug in -2, I would get a positive and a negative, so I'd get overall a negative. If I plug in 0, I get positive, positive, I get positive. And I plug in 2, I get negative, positive, I get negative. So again, we're looking at the second derivative. So a second derivative negative means f concave down, positive means f concave up, and negative means f concave down. So that tells me, okay, let's take a look at these points here. Do I have a change in concavity through them? Yes. So this is an inflection point at -1 something, and this is an inflection point at 1 something. And again, I would have to go back to my function and plug these values in. And if you remember, that was x squared over x squared plus 3. And so if I plug in -1, I'm going to get 1 over 4. I'm going to get 1/4, and I'm going to get the same thing if I plug in 1. So that's 1/4 and 1/4. Okay, so now we have a huge amount of information, which we now want to put into a sketch. Okay, so let's get ourselves a set of axes here. Whoops. Okay, that's better. So here we go. All right, so we saw a few things early on. We did see that 0, 0 was on the graph as an x and y intercept, so we'll put that there. We talked about asymptotes, and we found that y equals 1 was a horizontal asymptote. All right, so we also, what else did we see? We saw that 0, 0 was a relative min as well. So that means it must be bottoming out there. And we saw a couple of other points. We saw inflection points at -1, 1/4. So let me just put this here. I know it doesn't have to be super accurate. And 1, 1/4 there. Okay, so that's 1, 1/4, and that is -1, 1/4. Okay, so now I have to figure out how this all works together. Well, there's a bunch of different things happening at the same time, so there's a lot of redundant information in here, which is good because it can help me avoid any mistakes. So basically, if I look now at the concavity here, I saw that it was concave down all the way to the left. In the middle, it's concave up, and then it's concave down again after 1. So that means that basically it has to go from concave. So let's go forward from 0. So it's concave down. I'm going to get rid of some of this and redraw it. All right, it's concave down from a minimum at 0, 0 until it gets to 1, and then it's concave. It's concave up until it gets to 1, and then it's concave down, so it has to turn. And that makes sense because it eventually has to create the asymptote at y equals 1. The other way is very similar. It's concave up back to -1, and then it's concave down from -1 behind, and now you see that everything matches up, and we have a very good sketch of this function. I'll just label the inflection points there, and that's a very nice sketch of this function, which we got from all that information. And that's what we want. Okay, so let's look at another one. f of x equals x squared minus 6x plus 12 over x minus 4. All right, so again, let's start with the domain here. So rational function again, we'll look at the denominator, and obviously x can't be 4, so all real numbers except x equals 4. So we'll see exactly what's happening there later as we do more analysis. All right, intercepts. Okay, x-intercept, we'll set y equal to 0. Well, that's only going to happen if that numerator is 0. I'm going to go ahead and use the quadratic formula here. Negative b, so 6 plus or minus the square root of b squared would be 36, minus 4, a is 1 and c is 12, over 2a, so 2 times 1. Now what I'm going to see is I get 6 plus or minus the square root of 36 minus 48 over 2, and what I see automatically is that's going to be negative in there, so we're going to get imaginary roots here, and what that means is no x-intercepts. Okay, so no x-intercepts, that's fine, good to know. Sorry, the y-intercepts now. If I set x equal to 0, so that would give me y is 12 over negative 4, or negative 3, and so I have a y-intercept of negative 3. That would give me the point 0, negative 3. Alright, so now I know a point on the graph. Let's go asymptotes. Vertical asymptotes. So let's look back at our function here. Oh, obviously we have a place where the denominator is 0 and the numerator is not. So that's what we're getting. That's what x equals 4 was. Horizontal. To do my limits at infinity and negative infinity. So that would be, remember what this function was, it was x squared minus 6x plus 12 over x minus 4, x squared minus 6x plus 12 over x minus 4. Okay. Oh, so we do again have rationals. We have a polynomial over polynomial. Let's look at how these powers match up. So the numerator is dominating. That means this is going to be some type of infinity. So now we look, x going to positive infinity. The numbers on top from the x squared will be positive. The x's will be positive. That's positive infinity. Similar situation down here. Numerator dominating. But now I'm going to negative infinity. The numerator is x squared, so those will be positive, but the denominator as x will be negative, so this is going to be negative infinity. So I don't have any horizontal asymptotes, but this is going to be important information for later on. Okay, so how about let's start on the extrema. All right, I need my first derivative. Okay, so if you look back at the function, we need to do quotient rule. So that is going to be derivative of the top 2x minus 6 times the bottom x minus 4 minus the top x squared minus 6x plus 12 times the derivative of the bottom is 1 all over the bottom x minus 4 squared. All right, clean this up. So that's going to be 2x squared minus 14x plus 24 minus x squared plus 6x minus 12 over x minus 4 squared. And that is going to simplify to x squared minus 8x plus 12 over x minus 4 squared, which is going to be x minus 6, x minus 2 over x minus 4 squared. Okay, so there we have our first derivative, and we can start looking for critical numbers. So what we see is that we have, looking for f prime equals 0 or f prime undefined when f is defined. So f prime equal to 0, obviously 6 and 2. Undefined. Now f prime is undefined at 4, but the original function was undefined at 4, so none there. Let me make a note where f is defined. Okay, so now we're going to have to go to our chart for the first derivative, and we're going to put 2 and 6. We're also going to put 4 because that's a discontinuity. All right, we'll pick back up in a minute with this.